Okay, so today we're going to have a slightly different concept introduced. It's called differential equations with initial conditions. That's a really, really crazy elaborate name for basically we're taking the integral of something, except this time we have enough initial information to solve for what the value of c is. Because as you remember, hopefully, that whenever you take the integral of something, you always have to say plus c. In this case, we'll solve for what those c values are, because it depends on the initial condition. Anyway, here we go. So starting with some integration by substitution, should be substitution questions. So we'll go over a little bit of review of last class, and then we're going to look at expanding. We're going to rather expand on solving antiderivatives from the last two classes by looking at cases where an initial condition was given. In other words, we'll look at examples that will give us enough information to be able to solve for C. Also, we're going to look at a very bizarre application for differential equations that has to do with springs. For those of you who have taken physics before, at least the idea might be similar, but it's going to be a dramatically different setup than anything we've ever seen. We'll get to it when we get to it, though. Here we go. So we're going to start with an integration by substitution question today. I want you guys to give this one a try on your own. So pause the video here and I'll go over it in a second. All right, so I'm going to go over this one now. Remember, when we take care of integration by substitution, we should always start by figuring out what we're going to be substituting out. I always thought of it as like kind of the innermost function of this whole thing. In other words, it'd be the focus point from which chain rule would have come from. In this question, I think this x squared plus 6 is going to be our innermost function, because if you notice, this x squared plus 6 is taken to the power of 8. So in other words, we're going to say u is going to equal x squared plus 6. Remember, once we've identified a u, it's nice to figure out the derivative of that so we can at least start figuring out the differential dx. The derivative of u, which using Leibniz notation is du dx, is just 2x, because it's the power rule on that. Then we rearrange to solve for dx, so you can multiply by dx and then divide by 2x. Long story short, you're going to say dx is going to equal du divided by 2x. Now, we have enough information to start our integration by substitution. So if we substitute these things in, we're going to have the integral of, instead of this, it'll be u to the power of 8. I'll put that in brackets there, u to the power of 8 times by 2x, and then times by dx. But remember, dx is actually du over 2x. Again, this worked like a dream, just like the one from last class. We can say 2x is going to cancel out with 2x here. This is just going to leave us with u to the power of 8 du, taking the integral of that, of course. So this is just going to become u to the power of 9 divided by 9, because if you imagine taking the derivative of that, it's going to have a divide by 9 to cancel out. Plus c, I guess. That's really all we got. Last thing we need here, though, is u isn't part of our original expression here, so we should substitute back in what we had. So our answer to this question is going to be x squared plus 6, all to the power of 9, all divided by 9, plus c. That right there is going to be the integral of what we started with in the first place. And again, the nice thing about this is you can always take the derivative of this to check to see if it actually worked. Anyway, here's another one. Once again, pause the video here and I'm going to go over this one in a second. Okay, what you might have noticed if you gave this one a try is that finding your u is a little bit strange here. Often, like I said before, we try to find the innermost part of this function, but there really isn't. Both sides of this are kind of close to being the same thing. In this question, I opted to say, you know what, we'll say this is our u, just because it's a little bit more of a complicated component to this whole thing. And if that's our u, then our du dx, in other words, our derivative of u, is just going to be cosine x, and that's it, because the derivative of 1 is just nothing, right? Anyway, now let's solve for dx. So we'll multiply by dx over and divide by cos x. This gives us du over cos x equals dx. Now we have enough to start our integration by substitution. I'll just do it down over here. I don't think we'll need too much room here. So this is the integral of cosine x multiplied by u multiplied by du over cosine x, because that's our dx, of course, right? Hopefully you can see that this cosine x is going to knock out this cosine x over here. So we literally just have the integral of u du. Doesn't get much simpler in terms of integrals than that. This is just going to be u squared divided by 2 plus c. And that's about it, right? Of course, substitute back in what our u was in the first place. U was sine x plus 1, so we've got to be careful with our brackets here. The answer is going to be sine x plus 1 in brackets squared divided by 2 plus c. There you go. And that would be about it. It would be tough to do a question like this without integration by substitution, because it's really hard to tell where you would even start. Expanding this out, like multiplying this through here, wouldn't really help you too much, I don't think. But whatever. whatever, no big deal. Okay, so we're going to start on with this whole concept of differential equations with initial conditions here. But I want to just do a real quick preamble here. As we've seen before, if we have h of t representing a function that's the height of a falling object over time, so height is a function of time, then we could say that h prime t, the derivative of h, would represent the velocity of that object. So therefore, you could just say that h prime t equals v of t. Your derivative of your height is equal to your velocity function. Using Leibniz notation here, we can start doing some really weird things that prior to this unit, you would go, why on earth would we ever even do this? We could say dh over dt, so the derivative of h with respect to time, in other words, this is just h prime, right, equals vt. Like we've done in the last couple of days, we can actually take apart the Leibniz notation as if it was a fraction. So in other words, I could multiply by dt on both sides. So we could say the differential of h equals vt times the differential with respect to t, right? In other words, now if we took the integral of both sides, we have the integral of the differential of h equals the integral of vt with respect to t. Now, the integral of a differential is just the function you had in the first place, right? I know that seems like you'd say, well, why is it like that when this was the derivative in the first place? But it's because you need kind of a pointer to it, right? So if you had a dt here, you'd be taking the integral and be like, well, what's our pointer on that? Long story short, basically, you just have to understand that your height function is your integral of your velocity function with respect to time. And that shouldn't be a big surprise, especially given that we knew this. The derivative of your height is your velocity. That means your integral of your velocity is your height. Hopefully that makes some sense. Now, this leads us into initial value problems. So taking the integral of your velocity yields your height. But unless we are given more context here, we don't know the value of the constant c, right? Because if you took the integral of et, you're going to get some function for h of t plus c. And that plus c is kind of useless, right? Now, if the problem provides us some context, usually this is in the form of a known height given a known time. So I might say, oh, here's your velocity function, and also we know that at a time of 10 seconds, we have a height of whatever, right? This is what's called an initial value problem. And the reason it's an initial value problem is 99% of the time, we tell you the initial height when the time is equal to 0. So when we say, okay, your initial height was something, we say then time is 0 and your height is whatever we gave you, right? That's why it's an initial value problem. Not always called an initial value problem. Sometimes it's just like, it's a differential equation with conditions or something, but generally speaking, they're initial value problems. Anyway, that's not the main point of today. So we'll do a quick example here. This one doesn't really have much context to it. It's just kind of a plain math kind of problem. Solve for y if we know dy over dx, in other words, the derivative of y with respect to x is 4x, and that we know y is 7 when x is equal to 1. So this is one of those cases where calling it an initial value isn't probably the best idea, because again, it's not when x is 0, it's when x is 1. But still one way or another. Anyway, I'll walk you through this one. Since we know dy with respect to x, the derivative of y with respect to x is 4x, we could rearrange just like we did on that other slide. We could say dy equals 4x times dx. Okay. Now, if we took the integral of both sides, which you are allowed to do, if you do something on one side of an equation, you're allowed to do the same thing to the other side, generally speaking. The integral of dy is just y. So there we are. We got our y already. But the real question is, what is the integral of this right-hand side? Well, the integral of 4x with respect to x is going to be 4x squared, but we need to do something about that squared, because if it drops down, it would make it 8x, and we don't want that. So we're going to divide by 2 to get rid of that 2 when it comes back down. Then we also have to, of course, because we just took an integral of this, we have to say plus c. Technically, you could say plus c on both sides, but they'd be like c1 and c2. So why fuss with that? Just put 1c in there somewhere, and I always put it, of course, at the very last piece here. There's one more thing we can do here now, though. Well, actually, there's 2 more things. First thing we can do here is we can say, well, y equals 4x squared divided by 2. You might as well just say that's 2x squared plus c. That just cleans that fraction up. The second thing we can do here is notice we have an initial condition, or at least, some condition that was given to us in the first place. We know y is 7 when x is 1. Well, since we know what y is when x is something, we can just plug it right into this function that we got for y. This is not a complete function. We don't know what c is, but we can use this initial value here to solve for what c is here. So anyway, we can find this as 7 equals 2 times 1 squared plus c. Notice this would be 7 equals 2 times 1 squared is 2 times 1, which is just 2. So 7 equals 2 plus c. And bingo, bango, bongo, if you just subtract 2 on both sides, you got c is equal to 5. So long story short here, we were able to solve for c because we knew what our initial values were. So we can say our function for y, given that we knew this stuff, is y equals 2x squared plus 5, because c must have been 5, given those initial conditions. Awesome, right? So notice even with what we've done before with integrals, and I was always just like, oh, c is just some number, it could be any number, who knows what. It really doesn't take a lot more to find what c is. You just have to be provided with some context in the first place. So if I tell you some initial values, that's your hint. You're going to be able to solve for c. If I don't tell you that, well, then c is just c. No big deal. You always have to remember it's there. It's a really common thing for people to forget, but it is what it is. All right, so here's another example. This one's a little bit more complicated, mostly just because of the wording. If you want to give this one a try on your own, feel free, but otherwise I will go over it. The slope at any given point x on a function is x over 2. This function has a y-intercept of 3. Find the original function. Okay, a key word here, believe it or not, is slope. The slope at any given point x on a function, so a function, you can kind of assume this is a function f of x, a function of x. The slope is x over 2. Well, remember the slope of a function can be given by the derivative, right? The derivative just tells you what the slope of a tangent line anywhere on your function is. So your derivative just spits out what your slope is on your function at any given point x. So the wording of this is really the hardest part here. We can just say that we know that the derivative of our function, f prime x, is x over 2. We want to find the original function. So what we're looking for is we're looking for f of x. It's probably not too big of a stretch for you to say we just have to take the integral of both sides here. And obviously we'd be taking the integral with respect to x. So why don't we take care of that? If I take the integral of this left-hand side, we're just going to have f of x. That's not a big surprise. However, if we take the integral of the other side, x over 2, we have to assume, of course, we're doing this with respect to x. You could have found that by turning this into Leibniz notation and moving the dx over, although I'm sure you guys probably aren't too worried about that because the dx mostly just acts as a pointer. It's just pointing to say, hey, we're dealing with our x. Anyway, take the integral of that right-hand side. What we're going to see is we're going to have f of x equals, it's going to be x squared something. So x squared, we already had a divide by 2 there in the first place, but we have to take care of the fact that when the squared comes down using power rule, there'd have to be another 2 down there. So we'll multiply the denominator by yet another 2, and of course say plus c. Long story short, this is going to be f of x equals x squared over 2 times 2, which is 4, plus c. And if you don't believe me, take the derivative of that, and you will see it'll just equal x over 2. But we were actually given an initial condition. The y-intercept was 3. Well, the y-intercept, of course, happens at the point 0, 3. X is 0, y is 3. So we can just plug those numbers in to solve for our c value. Remember, y is always the same thing as f of x. So we can say 3 equals 0 squared over 4 plus c. Not a big surprise that 0 squared over 4 is just 0. So we can say c is equal to 3. And therefore, we can finish off our function. It's f of x equals x squared over 4 plus 3. And there it is, right? Not too terribly crazy, hopefully, but there it is. That's how we get our initial condition. Awesome. Okay, here's a gravity problem. This is going to seem more like a physics kind of lesson here. A person standing on the top of a 50-meter building throws a ball upwards at 10 meters per second. Given that gravity is 9.8 meters per second squared downwards, what is the displacement time function for the ball? Okay, holy smokes. Okay, this one's going to take a little bit more effort to it. I just want you guys to remember from previous lessons that if you have a function for your displacement or your height or whatever you want to call it, the derivative of that function is your velocity as a function of time. The derivative of that function, so the second derivative of your displacement function, gives you your acceleration as a function of time. For those of you who have taken physics, hopefully you'd remember that gravity's acceleration is constant. So in other words, it doesn't depend on a time value. Acceleration is just a constant number here. So this is what we can start with. We can say acceleration is equal to, well, it's 9.8 meters per second squared, but it's downward. So I'm going to call it negative 9.8. And I won't even put meters per second squared because we're dealing with this in calculus rather than in physics. So I don't really need units on my actual equations here. If we wanted to get a function for the velocity, we would have to take the integral of this, because hopefully you can see, since the acceleration is the second derivative, then the velocity is the first derivative, which is of course one up from that. So if we wanted the velocity, we can just say the velocity is going to equal the integral of negative 9.8 with respect to time. Okay, notice our function here is always with respect to time. If you called it x, it's the same idea, but I'll call it t for time. If we take the integral of this, it's actually a pretty simple integral. This is going to be negative 9.8t, because this would have been t1, and then of course when the 1 drops down and the t disappears, you're just left with negative 9.8. But then of course we have plus c. Now before we move any further, I want us to notice something that's given in the question. We were only given two little key pieces of information in regards to this whole function. We were told that the building's height is 50 meters. So we know our initial height when time is 0, our height is 50. We also know that the person who is standing on the top of the building threw the ball upwards at 10 meters per second. So when time is 0, our velocity was equal to positive 10 meters per second, because again, that was upwards. Upwards should be positive, downwards should be negative. Long story short, since we know that upwards velocity at a time of 0, why don't we throw that in here so we can solve for c before we even move on to a displacement function? So what we'll say is 10, positive 10 for our upwards velocity, is equal to negative 9.8 times 0, because it's our initial time, plus c. Pretty simple on this one. You just go negative 9.8 times 0. That'll cancel it out. We can say that c is going to equal 10. So therefore, we can say that our velocity function is negative 9.8t plus 10. Not too bad, right? We're starting to build this. All we had really was we had our 9.8 meters per second squared to begin with. Taking the integral of that helped us find the velocity. The plus c is just your initial velocity, just the plus 10. If it was thrown downwards at 10 meters per second, that would have been a minus 10, and so on, right? However, we're not looking for our velocity function. We're looking for our displacement function here. We needed to get our velocity function because, of course, that's already our first derivative. So if we take the integral yet again, that'll spit out a displacement function for us. So if we take the integral of both sides, we might as well just say that this is now d equals the integral of negative 9.8t plus 10. And I'll put that in brackets and once again make the note that this is with respect to time. Notice this is an integral of two things added together. That just means you can take the integral of each thing separately. I'll do it without writing it out a second time here. Long story short, though, we'll say it's d equals the integral of negative 9.8t, which should be negative 9.8t squared. But we need to do something about that squared, so we'll divide by 2 so that when it drops down, it's gone, plus the integral of 10, which of course is just 10t. And then we also need, again, a plus c. I'll use the same letters before. Some people like changing the letters up. You can say it's like plus, I don't know, f or plus g or whatever you want to say. But I'll just use another plus c. If that really bothers you, you can call the first one c1, and you can call this next one c2. Maybe that's what I'll do, just so I'm not being inconsistent here. Anyway, we do know from this question, well, first of all, I'll clean this up a little bit. D is going to equal negative 9.8 divided by 2. I believe that's negative 4.9. Yeah, negative 4.9 t squared plus 10t plus c2. But from here, we need to finish this function off because we don't know what c2 is. But the good news is we were told in the beginning that this started at the top of a 50-meter building. So in other words, when time is 0, our height is 50. So we can say 50 equals negative 4.9 times 0 squared plus 10 times 0 plus c squared, or sorry, c2. Long story short, you can just see that these are gone now, and we'll just say c2 is going to equal 50. So in the end, I'm totally running out of room here, but I'll do it way up the top here. Our displacement time function is d, or d of t, if you want to call it that, but I'll just say d equals negative 4.9 t squared plus 10t plus 50. And that right there is our function for our displacement. So pretty incredible. All we really started with was our gravity constant of 9.8 meters per second squared, and then how fast they threw the ball in the first place, as well as how high they threw the ball in the first place. And from that, we're able to generate a whole function. This is really, really incredible, actually. This already helps you build any of the questions that I would have ever showed you all the way back in like Math 20, I think, when we were dealing with quadratics. You can construct this stuff just from whatever little information you've got. Pretty fascinating. Calculus is pretty powerful here. Anyway, moving on. So at the beginning of the lesson, I kind of alluded to a really bizarre concept that I was going to introduce. this is it. You might want to pause a couple times when I explain it later on, but really I'll try to simplify it down to the only one thing you need to know. And the good news is this is on your formula sheet. It's underneath spring and pendulum differential equations, or some heading like that on the back side of your formula sheet, but we'll get to that in a second. So before we move on, one very special type of differential equation, an equation that contains a derivative inside of it, that's what that means, is the spring equation. The spring equation says the second derivative of y plus ky equals 0, just as long as k is greater than 0. What I want you to know, though, is y is a function in and of itself. It's a function that actually represents the stretch displacement of a spring or the stretch displacement of a pendulum, because the same thing works for pendulums. By displacement, we of course mean just how far it's moved from equilibrium position. That would be your y, as a function of time, which you could call x, or you could call it t, or whatever you want, right? So as time goes on, the displacement from its equilibrium point, this is the equilibrium point for the pendulum here, its displacement from the equilibrium point is changing at all times. It's going from positive to negative and then 0 and back and forth and back and forth. Same thing with a spring. If you had a spring, maybe I should have found an animated picture for this. That is a miserable spring, but you get the idea. Let's say you have like a weight attached to it, right? That thing is going to stretch, but it'll also bounce back up and down like a yo-yo, right? It'll go up and down, up and down. The displacement from whatever its equilibrium position is can be represented with this function. Anyway, long story short, I want you to notice that these formulas, this one's probably the easiest one to focus on. Both of them mean the same thing. This is still a second derivative. Notice that these formulas would imply that your second derivative is equal to negative k times y, just by moving that over to the other side. For those of you who've taken physics before, you might actually recognize this as being similar to an equation we had before. The spring force is equal to negative k times x, where x was your displacement, and k is your spring constant. For those of you who have not taken physics before, or even those of you who have and just don't remember the spring constant stuff, a spring constant just basically is a number that tells you how rigid or sturdy a spring is. The higher the spring constant, the more like hard it is to move, basically. If you have a really low spring constant, it's like a really flimsy spring that's going to move quite easily. Now, this might be difficult to discover, however. If I just gave you this right off the bat, you go like, what the heck? How do we get a function where the second derivative is just equal to the original function times some other number? Like negative k times the original function is the second derivative. That's kind of weird, right? Because you'd think that you get something other than a number that would come out of here. I want you to note this example, though. This is an example I've just kind of pulled out of thin air, sort of. Let's imagine y was equal to sine 2x. There's a reason I picked like a trig function in a second here. You'll see what I mean. If y is equal to sine 2x, the derivative of y would be cos 2x times 2, because the derivative of sine is cosine, so cosine 2x multiplied by your chain rule piece, the derivative of 2x is 2, so that popped out there. If you took the second derivative, notice now the derivative of cosine is negative sine, so negative sine 2x. Once again, multiplying by the derivative of the inside, so multiply by 2 again, now you have negative 4 sine 2x. Notice the original function was sine 2x, and the second derivative contains that function. So therefore, we could say that the second derivative is negative 4 times y. This same result would have been seen if we had used y is equal to cosine 2x instead. We would have seen another similar result if we had said something like y is equal to sine, I don't know, 5x, right? You would have also seen a similar result if you had like y is equal to 7 cos 4x, just throwing numbers in there, right? Because even if there was a coefficient out in front, that still would get carried through because it's just getting multiplied by whatever was inside that function each time. So it's still kind of there, it's just dissolved away in another number. Kind of an interesting pattern here. The fact that they were able to figure this out is pretty impressive. You don't need to worry about where it comes from. All you need to worry about, ironically, is kind of the scariest looking formula that we've seen here, but at least it's on your formula sheet. Using the facts from before, that whole thing that we just figured out right here, this whole relationship, we can state that the solution, or in other words, an expression for the function y, should always take the form y equals a times sine times the square root of kx. Notice that wasn't a coincidence here. 2 is the square root of 4. Any number you picked, as you multiply it through, you'd still get the square of that square root. So it is what it is. So a sine square root of k times x, notice x is not part of that square root, plus b times cosine square root k, also times x, where x is also not part of that square root. Now, keep in mind, k has to be a positive number. If it wasn't a positive number, you'd have a square root of a negative, and we all know how that works. It doesn't, right? But A or B, or even, I guess, maybe even theoretically both. I mean, if you had both, you wouldn't have anything going on here. Either A or B, they might be equal to 0. Maybe they won't be. Maybe some of them will be not 0. Like maybe they'll both exist there. I don't know. Who knows? It'll depend on your initial conditions. Long story short, whenever you see a spring or a pendulum differential equation and you're trying to solve for a function for the displacement of the spring or pendulum, so in other words, you're solving for y, your answer is going to take this form. And that's always what you should start with. Sometimes you'll have to take the derivative of this. Good idea to take the second derivative sometimes too, just to check to see if it worked. This is a lot easier seen with an example, but it is a very bizarre situation that we still need to understand. Anyway, here we go. So we're only going to do one example today. I'm going to walk you through it because there's no way, no offense, there's no way we're going to pick that up right off the bat here. Maybe there is. Maybe you could try this and say, hey, maybe I got this, but we'll see. So the displacement, S of t. I don't know why we're using S this time instead of Y. It's whatever. Anyway, S of t of a pendulum from the center, that's just equilibrium, of course, is given by the formula S double prime plus 9S equals 0. We are given the initial condition that at t is equal to 0, we have S is equal to 0 and S prime is equal to 1/2. Find the original displacement function S of t. Before I go anywhere with this, it just kind of like popped in my mind as I was reading this. For those of you who have taken physics, you might be saying, okay, cool, like what do we care? We know how to use the physics formulas. Why do we care about this? In physics, we just called this displacement an x. We didn't care about it as a function of time. We only looked at it like little instances at a time. We said, okay, here it is at this time, here it is another time. With calculus, we can actually get a function that represents how that function changes over time and how it moves back and forth, back and forth. That is a lot more powerful than anything we ever did in physics. But I digress. Here we go. So we're looking for the original displacement function, S of t, right? We know that it follows a spring slash pendulum formula here, where we have a second derivative plus a number times your displacement function equals 0. That means we know, and we don't have to show any work for this. It's just a thing that we'll accept as fact. We know that our function S is going to take the form A times sine times the square root of k. Well, the square root of k, this is k right here. Square root of k would be the square root of 9, so it'll be 3 times t, because we notice it's a function of time, plus b cosine, excuse me, the square root of k, so 3 times t. We know our function is going to look like this. The real question, though, is what are the values of a and b so that we can actually confirm whether this worked or not. Okay, so in order to find a and b, we have to look at what our initial conditions are. We know the initial condition that at t is 0, so when time is 0, we have S is 0, your displacement is 0, and S prime, which I guess would be your rate of change, your displacement, in other words, your velocity of your function, is 1/2. Well, notice since we're given t is 0 and S is 0, we can just plug that in for our first initial condition here. We can say, okay, S is 0, we say 0 equals A times sine times 3 times 0, or sorry, sine of 3 times 0. 3 times 0, though, is just 0, plus B cosine 3 times 0, which is again 0. Well, here's the good news. Sine of 0 and cosine of 0, remember we're in radian form, not that it matters here. Sine of 0 and cosine of 0, we can actually calculate those. For those of you who are really keen on your unit circle, you might remember that sine of 0 is actually just 0. So this whole thing is 0. Again, cosine of 0, if you're really keen on your unit circle, you might remember that that's just equal to 1. So therefore, we can actually fix this up here. We can say 0 is equal to, well, this whole thing is 0 because A times 0 is just going to be 0. So it's going to equal B times 1, which is just B. So look at that. We just found B is equal to 0. So guess what? If we just figured out that B is equal to 0, we can just say that S isn't even this whole big chunky thing. We just know S is A sine 3t, because B is 0, it knocks out the rest of that. Now, if you're wondering right now, okay, you found B is 0. What about A? Well, we weren't able to determine A from this question because as soon as we figured out sine 0 was in this, sine 0 multiplied A by 0, that totally nullified it no matter what it is. We don't know what A is yet. We'll have to find it some other way. And there's no way of determining it just using this first function here with the information we've got. So unfortunately, we're just going to have to do a little bit more work on this one. Notice we only use the initial condition S is 0. We were also given the initial condition S prime is 1/2. It's a good thing we dealt with this first, because notice we were able to trim our function down so it doesn't contain b cosine 3t. That means right now, if we were to take the derivative of s, which we'll just call s prime, we just have to worry about taking the derivative of a sine 3t. Well, a is a constant out in front, or a coefficient, I should really say. A is a coefficient out in front, so it's not going to affect our derivative. It's just going to like hang out on its own. So let's take the derivative of sine 3t with respect to time. The derivative of sine is cosine, so we know we have a times cosine 3t. But then we have to multiply this by the derivative of the inside of the function. The inside of the function is 3t. The derivative of that is just 3. So we know our derivative function is 3 times a cosine 3t. Now, we were given the initial condition that at a time of 0, our first derivative is 1/2. So let's actually apply that now. We'll say at a time of 0, first derivative is 1/2. So we have 1/2 equals 3a times cosine 3 times 0, which is just 0. Just like before, remember cosine 0 is 1. So we might as well just say 1/2 is equal to 3 times a. And then we're almost here to solve for a now. We can just divide by 3 on both sides, and we've got a. The question is, though, 1/2 divided by 3, kind of a messy number. If you think of this instead as multiplying by 1/3 on both sides, it becomes easier. This is 1/6 equals a. Therefore, if we are coming up with an original displacement function s of t, we can write this as s of t is equal to 1/6 sine 3t. And that solves our problem right there. If you don't believe me that it works, you can always double check it. You can take the second derivative of the function and then add 9 times this. You're going to end up finding that it does indeed work. It does kind of look like a train wreck, I'm not going to lie, but yeah, it is what it is. So these spring pendulum problems, the bottom line is always start, when you see that you've got one, start with this formula. We pretty much always give you the k value. So k is 9 here, the square root of 9 was 3. And then just use your initial conditions however you can. You just have to be pretty keen on the fact that sine of 0 and cosine of 0 are 0 and 1 respectively. Whew. Anyway, that was a long video today, guys. I apologize for that. I mean, most of them seem to be around half an hour, so whatever. For practice, lesson 2, differential equations with initial conditions. That's in your work booklet, of course. Remember, the answers are on Google Classroom. You can find them up at the top of the page. A bit of a heads up, you can only do up to question E right now. We'll continue this topic next time we have a class. And of course, also make sure your previous handouts are done as well, because integrals, like everything else, seems to build on itself. Anyway, if you need any help, make sure you pop back into the Zoom and ask. Best of luck.